We talked about a force developing between two charges, and in the case of charges with the same sign, we have repulsion, and charges with opposite sign, we have attraction. So this electrical force between two charges is an electrostatic force, or we can call it Coulomb force, that's between two stationary point-like charged particles. So if we look at these point-like charged particles Q1 and Q2, force exerted by Q1 on Q2 is called F12. So since this is a repulsive force, it will be radially outward in the direction R12 hat, where R is a radial vector pointing from charge 1 towards charge 2. R is the distance between the two charges, and there will be an equal and opposite force exerted by charge 2 on charge 1, which will be in minus R12 hat direction or R21 hat direction. Because they have the same sign, this is a repulsive force. When we have a positive charge and negative charge, the direction of these forces will reverse. Force exerted by 2 on 1 will be in the R12 hat direction. Force exerted by 1 on 2 will be in minus R12 hat direction, pointing towards Q1. Therefore, these two will be attracting each other. Now F12, force exerted by 1 on 2, is equal to minus the force exerted by 2 on 1. Why? Because we have Newton's third law, action-reaction. So there should be an equal and opposite force acting on the other part of the system. Now, what is the magnitude of this force? It's Coulomb's constant K, the product of the two charges, Q1, Q2, divided by the distance between the charges squared. So it's R squared. And as you can see here this for the positive charges, this will be in R12 hat direction. So K, Q1, Q2 over R square, R12 hat direction, that's the unit vector, is F12. So F12, once again, is the force exerted by charge 1 on charge 2. Now, what is this Coulomb's constant K? It is 1 over 4 pi epsilon 0, where epsilon 0 is permittivity of free space. The permittivity of free space has a value 8.85 10 to minus 12 Coulomb square over Newton meter square, and K is approximately 9 times 10 to 9 Newton meter square over Coulomb square. So this is known as Coulomb's constant. Now we have talked about charge transfer. Charge is transferred in units of electron charge, 1.6 10 to minus 19 coulombs. So all of these point charges will have an integer multiple of the unit charge, which is the electron charge. It can be positive or negative. Okay. Now, if there are more than two charges, then the force on a given charge will be the sum of all the forces due to other charges. So we will consider the contribution from the other charges in the distribution and add them up. So let's talk about an example here. We have three charges here. Q1, located at the origin, it's a negative charge, it's minus E. And Q2, another minus E charge, located at an angle 45 degrees with respect to the y-axis in the second quadrant, and we have Q3 on the x-axis, located at a distance r from charge Q1, and that has charge plus E. So distance between Q1 and Q2 is r, Q1 and Q3 is r, but there is an angle 45 degrees for the R12 hat direction, so that's going to be making an angle 45 degrees with respect to the y-axis. So what is the net force acting on charge 1? So we will consider basically the contributions from the two other charges. Force acting on charge 1 will be equal to force exerted by charge 2 on charge 1 plus the force exerted by charge 3 on charge 1. So we have to add them up. So since this is a vector equation, we need to consider x and y components. X component of the force acting on charge 1 is force exerted by charge 2 on charge 1 x component plus force exerted by charge 3 on charge 1 x component. On the other hand, force exerted on charge 1 F1y y component will be force exerted by charge 2 on charge 1 y component. Now, since charge 3 is on the x-axis, there won't be any contribution from charge 3. Okay, let's calculate the x component of the force exerted by charge 2 on charge 1. So you can see here a force exerted by charge 2 on charge 1, because they have the same sign, will be first a repulsive force. It will be pointing away from charge 1 and in the R2 1 direction. So this is basically force exerted by charge 2 on charge 1. Okay, so this basically makes an angle 45 degrees with respect to the x-axis. You can see here, it's the same angle that will appear here. So if we take its x component, we have to multiply it by cosine 45. Now the force between the two charges, two negative charges, will be equal to Coulomb's constant K, Q1, Q2 squared, E squared, divided by distance between the two charges squared, R squared, and it's in the positive x direction, cosine 45 degrees for the x component. Now, for F31x components, you can see that this is a positive charge, this is a negative charge, so therefore we will have basically an attractive force. So the negative charge will be attracted towards the positive charge. This will be the force exerted by charge 3 on charge 1, which only has an x component, that is equal to k e square divided by r square, because r is the distance between these two charges. So we will find that we have 1 plus cosine 45 is 1 over square root 2, or square root 2 over 2. 1 plus 1 over square root 2, k e square over r square. Now for the y component, we have here you can see we will have a y component of F21, which will be in minus j hat direction. So this will be sine 45 now. So this is going to be k e square over r square sine 45, which is 1 over square root 2 k e square over r square. So we're now ready to write the total force acting on charge 1. So this is going to have an x component, 1 plus 1 over square root 2 k e square over r square in I hat direction, and then minus k e square over r square j hat direction. So you can see here, this is my I hat direction, and this is my unit vector on the y-axis, j hat direction. So this will be the final answer for the net force acting on charge 1. Okay, so in summary, we have introduced Coulomb's law. So the electrostatic force between two charges has a magnitude, Coulomb's constant, the product of the two charges divided by the distance between them squared. So we're talking about two stationary point-like charged particles, the electrostatic force or Coulomb force developing between them. This force is a force couple, basically force exerted by 1 on 2 is equal to minus the force exerted by 2 on 1. So we have Coulomb's third law. They will be in opposite directions, but will have the same magnitude, action, reaction. And in the case of two opposite charges, these force vectors will be pointing towards the charges. In the case of two charges with the same sign, away from the charges. Now this unit vector r12 hat points from charge 1 towards charge 2. So once again, F12 means force exerted by charge 1 on charge 2. So you can see F12 is in the direction of r12 hat for this case. The Coulomb's constant is related to permittivity of free space, 8.85 10 to minus 12 Coulomb square over Newton meter square, 1 over 4 pi epsilon 0, that's 9 times 10 to 9 Newton meter square over Coulomb square. And these point charges are integer multiples of the electron charge, 1.6 10 to minus 19 coulombs. And when we have more than two stationary charges, the force on a given charge will be the vector sum of all the forces due to other charges. And in this example, we have force exerted by 2 on 1 pointing in the diagonal direction, diagonally out from Q1, so making an angle 45 degrees with respect to the x-axis. And force exerted by 3 on 1 points towards Q3 because these two charges have the opposite sign. F31 only has an x component, which is ke square, this is minus e plus e, ke square over r square in plus I hat direction. And the force F21 has an x component, ke square over r square in with a cosine 45 in plus I hat direction. So cosine 45 is 1 over square root 2. So this gives us 1 plus 1 over square root 2 ke square over r square. For F31, this is just ke square over r square. And it will be pointing towards Q3. So it's going to be plus I hat direction. But for the y component of this force, we have there's no y component for F31, but F21 has a y component, ke square over r square sine 45 in minus j hat direction. So we can put this result all together here. The vector sum of these two forces is basically F1x I hat plus F1y j hat. So in this, in taking care of Coulomb's law, first we dealt with the magnitudes of the force components here, and then the directions are taken care of by using these unit vectors I hat and j hat. So no need to worry about the signs of these charges in calculating the magnitude. We can talk about the direction by considering this piece of information that if the two signs are equal, well, that should be a repulsive force. If the two signs are opposite, then we will have an attractive force. So that's what we should see in this vector diagram.